Alright, so in this video I want to show you how to set up a linear programming model in Excel and solve it using Excel Solver. So let's first quickly look at the slides. So we go to Excel, and again, if you remember, we essentially need to set up an objective function that we want to maximize. That is our profit function. And we have our constraints. And below you see the conversion or the translation of those functions into Excel. And so we need to tell Excel we have certain decision variables that you need to choose. We need to enter a couple of formulas that Excel needs to evaluate, and we need to let Excel know what the constraints are. And you can look at those slides on the side, but I think it's easier if you just see how I set up the equation from the very beginning. So what I need is, I basically need just this one here. That's all I need in order to set it up in Excel, and I quickly copy this and I'll just paste it here so I can look into it into Excel. But let's still keep on going. So we have to enter a couple of formulas in the constraints, so that's the idea. Once we set it up, we call on Excel Solver. I will show you how to install that, and then we can run it, and if everything goes well, which it should, then Excel Solver should tell us that the optimum combination of Bernoullis and Nightingales is 8 and 2. And this is then what we will see. So that once we run the Excel Solver, we should see the optimum amount is 8 and 2. And then there are a couple of other reports that Excel provides. They are the answer report, the sensitivity report, and the limits report. We will go over them as well. And yeah, this is what they will look like. So the answer report is pretty self-explanatory. It tells you the final value of the objective cell. So what we expect here would be 8 and 2 for the Bernoullis and the Nightingales. Then it also shows the optimum parameter values, like the decision variables. So we should see the total optimum. And it also tells you the constraint values and whether they are binding in the optimum or whether the solution has some slack. I go a little bit faster here because it will become clear once we see the after we program the model. But then we also take a look at the sensitivity report. There, what is important are things like reduced cost, allowable increases and decreases, and shadow prices. That's important. And yeah, I'll just show you that so that you can see what to expect as we program it in Excel. And the last report is that is also belongs still to the sensitivity report, explaining allowable increases, decreases, shadow prices, and the final report is the limits report, which basically tells you how much each decision variable contributes to the total profit. So those are the slides, and as I said, it will become clear once we go through the model and we program it ourselves. So all we need is this information. Okay, so let's start setting that up in Excel. Okay, I'll make it a little bit bigger. Okay, so anywhere we have to tell Excel what are the decision variables. So I just write here decision variables. Well, our decision variables are Bernoullis and Nightingales. So let's write here Bernoullis and Nightingales. Okay. And then let's fit to content. Okay. So in the next row, I write the optimum quantities. And I indented a little bit, so because it still belongs somewhat to the first section, which is concerned with the profit. And these are cells, the optimum quantities. So in this case, cell C4 and D4, they will be ultimately chosen by Excel. So, okay. And then we have the unit profit. Those would be the parameters A and B from the general formula. So that's the 10 and the 10. That should be a 10 here. I don't know why that's a 0. So that should be a 10. It looks like I had here a typo, but this is 10. Okay, so the unit profits are 10 and 10. And now I create a formula which gives us the total profit. I'll just call it total profit. So the total profit is equal to the optimum quantity for Bernoullis times the unit profit per Bernoullis plus the optimum quantity for Nightingales times the unit profit per Nightingale. So now it says 0, but if I enter here 1 and 1, you can see that this cell immediately adjusts. So let's also indent quickly this one, and let me fix the what I copied. There seems to be a there's a 0 missing. Okay, so that's fixed. Okay. So let's format it a little bit nicer. So this cell here, the optimum quantities, where I just inserted 1 and 1, these are calculations that Excel will do. So I use Excel's cell style, and I say, well, this is a calculation that Excel will take care of. You can format it differently, it doesn't really matter. And or we can say, if we want to, maybe that's better, that's an output. We can also say that's an output that Excel will generate. It doesn't matter how you format it. But the unit profits, that is something that you need to input. So that, let's call that an input cell. And the total profit, that is a calculation, that's a formula, and we need to enter. So now the point here is that, if this changes, total profit changes. And again, these two cells C4 and D4, those are cells that Excel will play around with in order to find the optimum. So this is basically our profit section, and now we turn to the constraints. And again, now we have constraints for the Bernoullis and the Nightingales. So we have 3 constraints. We call them cloth, glue, and plastic. And again, I indented a little bit so that it looks nicer. And now I need to input those production parameters. So that will tell us if I want to produce 1 unit of Bernoulli, I use up 2 units of cloth. If I want to produce a Bernoulli, it uses up 1 unit of glue or 3 units of plastic. So the 213 goes into here, 213. The production of a nightingale requires 1 unit of cloth, 4 units of glue, and 6 units of plastic. And this is also an input. You need to input that. That is information which is somehow given. Then I typically recommend to put here next a sign, so write sign, and that will tell us what the constraints is. So we have here available, and then all the constraints are less than or equal. So let's write it like this, less than or equal, less than or equal. And the available amount of resources is 18, 20, 36. 18, 20, and 36. And this is also an input field, so that is something which is given, but okay, that may change. And then you could enter maybe something else. If you have more cloth, you can change that later. Okay, so that is the total available. And actually what I forgot is I need to insert here another column, and I call it total usage. And actually let's do it like this. And here I put total usage. And now I need to enter again a couple of formulas. So what will be the total usage of Bernoullis? Well, the total usage of Bernoullis will be, if Excel finds the optimum number of Bernoullis is 2, then we have to do 2 times 2. And if the optimum number of nightingales is 1, well, that uses up another 1 times 1. Okay, so now you can see if Excel, for example, finds that the optimum combination is 1 nightingale, then the total usage should be actually 1 nightingale. So let's do it again. 0 times 2 plus 1 times 1, and now we should see there were 1. And if we add here another Bernoulli, we should see 3. And that's correct. So that formula, total usage, will tell us how much we actually use up. Okay, let's do that next for glue. So that formula would be whatever Excel decides is the best number that we should produce of Bernoullis times the amount of glue plus the optimum number of amount of nightingales times how much that uses up of glue. So that is 6. 1 times 1 is 1 plus 4 times 1, that's 5. Why is that? Oh, that's not a plus. So you also need to check, of course, that your formula is right. So now we have 5. 1 times 1 is 1 plus 1 times 4 is 5. And if that is 2, it should go up to 9. Okay, that's correct. And the last one is optimum quantity of Bernoullis times how much plastic that uses plus the optimum quantity of nightingales times this. So here we should see 15. Okay, that's correct. So this total usage is also calculation. Okay, so again, and I think the last one is, so we don't need this cell, we can Okay, so now we have the total profit function, which has a formula, and we have our constraints, and that looks very similar to, well, there's the zero still missing, to what we had here. So, and now we can use Excel Solver. And what we do is we just initialize everything with 0 and 0. Okay. So now in order to activate Solver, you go to Data, Data Analysis. If you don't see that, you have to go to File, Options, Add-ins, and then at the bottom you see here Excel Add-ins. Go and make sure that you have Solver Add-in activated. Then we say OK. And so let's colon Solver. Okay. So now this is pretty self-explanatory. So what is the objective function? Well, my objective function is the total profit. So you click in here, which is cell E4 in my case. And you can tell Excel, do you want to maximize, minimize, or have a specific value? Well, we want to maximize. So then it says next, by changing which variables? Well, we want Excel to play around with these values. So what Excel will do is it will say, okay, let's try 1 and 0, 1 and 1, 1 and 2, 2 and 2. And then let's just show. So Excel will say, okay, maybe 1 and 1, that's a good solution. And then Excel will know, okay, total profit is 20. And next Excel will check, oh, okay, the total usage is 3, 5, and 9, which is less than 8, 20, and 36. So maybe I should do more. Okay, let's do 10 here. Then, you know, Excel sees, oh, okay, now we have a total profit of 110. But that's not good because I don't have enough plastic. So I need to go down again until I find maybe 8 and 2, what we derived earlier. So that's the idea. So let's go back. Data analysis, Solver. So we start by telling Excel, maximize this column by changing these two cells, which is C4 and D4. And now we have to add the constraints. So we add the first constraint. Excel, we have to say that the total usage of cloth needs to be less than or equal to the 18. Now let's add another constraint. The total usage of glue needs to be less than or equal to 20. Let's add the third. And total plastic needs to be less than or equal to the 36. Okay, so now we can see those three constraints. There is a shortcut whenever the sign is the same, like here all the constraints are less than or equal. Then we could also just delete those quickly. We could also tell Excel the shortcut that all those three, we just highlight in all three, we highlight all three total usages, and then we highlight and drag down the corresponding available. And then we just say OK. So that is the same. Then we typically want to check make unconstrained variable than negative. That basically means that we want to avoid that some of the optimum values are negative. So that we tell Excel, just limit your search to positive numbers. under certain conditions, like especially quadratic relationships, an optimum value might be negative. The last thing we want to do is we want to select the solving method to simplex linear programming, because everything is linear. That will use less computational power, although it wouldn't be a big deal in a problem set as simple as that. Okay, so now we have programmed everything, and what we could do next is we click solve, and then we should see that here Excel finds the optimum quantities of 8 and 2, which were the quantities we also derived earlier graphically. Okay, so let's see what we get. Let's solve. And that opened a new window. And you can see Excel identified indeed the optimum quantities as 8 and 2. And what you can see is also here are additional reports: the answer report, the sensitivity report, and the limits report. If we click on these and say OK, Excel will open up here new sheets with output, which provides additional information. So let me say OK. So you see we have now the answer report, and we have a sensitivity report, and we have a limits report, and here we have our model. So what I will stop now here, and what I will do is next I will add a graphical illustration to the solution, so that the solution that we get, if we change certain parameters, will automatically adjust. But for this video not to get too long, I'll quickly stop here, and then I'll start a new video where I build on this one by adding an interactive visualization of the linear programming model, similar to the graph that we derived earlier. But I'll just stop here, and then we keep on working on this exercise in the next video.